Okay, so we're working on. I'm trying now to use the document camera for some of these. We're in chapter 5, the best basis. And so, just to give you a little bit of motivation for what we're going to be doing, suppose that I've got a bunch of data in R2, but it's not just a random distribution in R2. It just happens that the data lies very close to a line. By the way, in this case, our line has to be through the origin. So you can imagine, right, that my data would be mean subtracted first, right? So just to make sure that the mean of the data goes through the origin. Okay, so now we're looking for how to represent the two-dimensional data in a lower dimension. And we see here that we should be able to write it as one-dimensional data, right? Because it's really along the line. There's going to be a little bit of error there, right? But mostly it's along the line. So suppose I've got a point out here, x. X is in R2, or more generally, x is going to be assumed to be in Rn. And we assume that there's some low-dimensional coordinate system where we can basically represent or capture most of x, right? So in this case, the one-dimensional coordinate system, let's say, is in the direction of u, where u is a unit vector. Okay, and so then the data projected to u, the projection of x onto u, we remember that, x dot u over u dot u times u. But of course, if we simplify this a little bit and assume that u has unit length, and then this is still in R2, right? This is the two-dimensional data point. But it's really this piece right here that's of interest. These are the coordinates, and the coordinates are in R1, the reduced dimension. So this is the coordinates are the reduced dimensional space. This is the reduced dimension, right? Or I guess we could say it's the reduced representation, reduced dimensional representation, something like that. Okay. So we can just forget about the u for now and just work with x dot u. So we would, we would start off with x1 through xp in Rn. And then if we were able to reduce these to one dimension, right, that would be reduced to, well, the coordinates. Maybe we'll just call them C1 through CP. And these are each in R1, right, where each of these is xi dot u. Good. What would this look like in the higher dimensional space? So if I have x1 through xp in Rn, then what I would be doing is I'd be looking for a basis, a new basis for my for a k-dimensional subspace of Rn, for a k-dimensional subspace of Rn, right, where I can capture most of my data. Okay, and so again, I'm going to assume that my data has been mean subtracted. So the mean of the data is, by the way, the mean of the data is a vector in Rn, right? And so those have been mean subtracted, so the mean of the data is 0. And so your data, I'll draw a little picture of Rn here. We're thinking of the data as being a cloud, right, centered at the origin. Okay, we're trying to find a low-dimensional subspace. So we want to find a basis, let's say u1 through uk, right, that spans our space, that spans the space of the data. Of course, if it spans the space of the data itself, right, we would be really lucky. Normally, there's going to be some error attached. We'll talk about that in just a second. But some things about this basis that are going to make this work is we will assume orthonormal. So if I line these vectors up in a matrix U, What's the dimensions of U? Each of my vectors is an Rn, but I've got k of them, so this is n by k, right? And so the coordinates now, the low-dimensional representation that I'm looking for is going to be the coordinates of the data. And so if I gather my data points in a matrix X, and by the way, I'm really kind of anal about this. Be sure and check your dimensions. X must be what? N by P, right? And so in my low dimensions, in the coordinates, what's the dimension of the data going to be? I've got P data points, and I want to be in RK, right? So that's going to be either K by P or P by K. Okay, so the coordinates of the data is going to be U transpose times X. Let's double check that. That's going to be K by N. That's going to be N by P. And so the coordinates are going to be K by P, right? And so what does that represent? Again, that's P points in RK. P points in RK. Very good. And so this is our goal then. So given a set of data in Rn, I want to find I guess we're starting here. I want to find a k-dimensional basis so that I capture somehow most of the data. So we're going to have to define that, what we mean by that, and we will do that shortly. I just wanted to give you kind of an overview of what we're doing. So given data, I want to find vectors for the best k-dimensional subspace representing the data. There'll be a little bit of error, but we'll have to figure out what the error is going to be. Good. So I don't want to give away the punchline, but I think it's important just to kind of keep in mind what we're going to be showing. We will show that the best basis is given by the first k eigenvectors of the covariance matrix for the data. So it's the eigenvectors of the covariance matrix that we're after. But numerically, we never want to compute the covariance matrix itself because, we'll talk about it later, but there's a lot of numerical error involved when you're computing that. So normally you never do that. So rather, it turns out that these are the left singular vectors of the SVD of X, the data matrix. Okay, and again, those are the best basis vectors. So we're going to need to prove that a little bit. It's kind of a magical statement right now. All right, so how are we going to show that? First off, let's remember what the covariance matrix is, just to give us a reminder. So a few things first. The covariance matrix, so X is N by P. So we're thinking of that as P points in Rn, and so our data is stored column-wise, right? And so I guess right now we won't assume that these data points are being subtracted when we first define our covariance. So this is the covariance between the ith and jth. Now, when I say that, what does the covariance mean in data like this when you have p points in Rn? Well, the covariance is between the ith and jth dimension, right? So we covary the I and j dimension. And that means it's the covariance between rho I and rho j of the data as defined here, right? Because our dimensions are in the rows. Okay, and so therefore the covariance matrix is going to be 1 over p minus 1 times the sum from, let's say, k equals 1. I guess I'm not counting like Python yet, from 1 to 1 to p. And now I'm covarying the row I and row j. So what are elements in row I? That would be x, I, k, right? That's row I, the kth element of row I. Times x, j, k. Huh? Oops, you know what? I forgot about the mean. Forgot the mean. So if the mean was 0, you would compute this. Otherwise, you would compute equals 1 to p. X, I, k minus the ith dimension of your mean, right? And that's x, j, k minus the jth component of your mean, right? Because the mean is also a vector in Rn. Good. Okay, and so notice that if you think about this as a picture, right, you're taking matrix X and you're taking the ith row of that, and then you're taking it times the jth row of x of x. But notice that the jth row of x is the same as the jth column of x transpose, right? And so if this is n by p, this one is p by n, and you end up with an n by n matrix. So C can be written in matrix form as just x times x transpose, right? But this is assuming that the data is mean subtracted. Good. I've run out of time, but we want to show, oh, excuse me. We also wanted to just take a note that this can actually be written as 1 over p minus 1 times the sum k equals 1 to p of x, the ith column, transpose, xi, oops, sorry, oh no, it's xi, xk, well, gosh darn it. I'm running out of time, so I'm getting nervous here with my notes. This is I. Let me rewrite that. I'm running out of time. Let's see if I can get it right this time. I want I equals 1 to n x I transpose. The idea here being that this is an n by n matrix, right, that you're summing together. Good. So see if you can get these two things to match up. Actually, it comes right out of this, and I don't want to speed up my talking anymore. I'll just stop here and we'll take a look at it in the next video.